All right, so we're going to start, pick up where we left off, and we're going to start with talking about unit vectors again. Can someone remind me from yesterday, what does it mean if a vector is a unit vector?
One unit.
What? Yeah, 1 unit in, like what do you mean 1 unit?
One unit.
1 unit, like,
To the right.
the what?
To the right.
No, it doesn't have to be to the right.
1 unit long.
1 unit long. I don't care if it points up, down, left, right, north, east, southwest, whatever you want to do. But it's got to be 1 unit in length pointing in any direction. Right? So when we have a vector that's 1 unit long, we call it a unit vector. And what I want to look at is what happens if I give you like that vector in black and it's too long. I want to make it shorter to turn it into a unit vector. So I want to figure out a formula that can take any vector and change it into a unit vector. What did we learn yesterday we can do that changes the length of a vector, but doesn't necessarily change the direction?
Add 2 vectors together.
Possibly, you could add 2 vectors together and it might not change the direction. I'm thinking of something else that is more designed to make something longer or shorter. Scale, yes. So that's when we multiply a number by a vector. So what we're going to be doing here is I'm going to give you a vector, and you're going to have to scale it to make it longer or shorter so it's exactly 1 unit. So let's just try a few examples without even vectors. If I gave you something that had a length of 5, what would you have to scale that by to make it so it had a length of 1? You'd have to scale it by 1/5. So what we're doing is we're looking for a pattern. I'll give you a few examples with numbers, and then see if we can come up with a formula from the pattern. Okay. What if you had a vector that was 1/3 of a unit long?
3.
You'd have to scale it by 3. What if you had a vector that was 4/5 of a unit? You'd scale it by 5/4. So if you had a vector that was x units long, what would you scale it by?
Negative x.
So if it was 5 units long, would you scale it by -5?
No, 1 over x.
1 over x. Yeah. So the pattern is when you have a vector and you want to turn it into a unit vector without changing its direction, you scale it by the reciprocal of its length. And if it already is 1 and you scale it by the reciprocal of 1, well, then it stays the same. Right. So let's try an example of that with an actual vector. Let's say I had the vector, let's do like 5, 12. Okay, think about the vector 5, 12. It goes right 5, it goes up 12. Okay, it's definitely not going to have a length of 1. So the first thing I have to do is figure out what is the length, and how do we find the length of a vector?
The Pythagorean theorem.
Yeah, use the Pythagorean theorem. Okay, so Christian, can you set up the Pythagorean theorem for me there?
Question?
Yeah.
5 squared plus 12 squared.
And when you add 5 squared and 12 squared, what do you get?
169.
169. And the square root of 169?
13.
13. So I know that this vector is 13 units long. So I need to scale it by what? 1/13. So to turn that into a unit vector, you're going to scale it by 1/13. So it's kind of like you're going to distribute this 1/13 out to each number. Right? So you can either think of it as distributing it out to each number, or in this case, it's really just dividing each number by 13. So the new vector would be 5/13, 12/13. That would be, this picture right here is basically what's being represented. You took the vector in black, you scaled it down 13 times smaller to make the vector in red. So I'll write that down as a formula now. So this is what we just did. We found a new vector. It pointed in the same direction, but instead of being 13 units long, we made it only 1 unit long. And the formula was to take our vector, and we essentially divided it by the magnitude. In this case, the magnitude was 13, so I divided each number that I had originally by the length that we calculated, by 13. Which is exactly the same thing as doing this. Whether you multiply by a fraction or you divide, it comes out the same. Okay. It might not always be 1/13. It could be 1 over whatever you get when you do the Pythagorean theorem. All right, so let's try another one. So this time they're giving us the vector 3i minus 4j, and they want us to turn it into a unit vector. What's the first thing that we have to figure out?
The length of it.
Right, we need to find the length of the vector they gave us, because maybe it already is a unit vector, and we don't have to do anything. If it's not, then we will. So, Maddie, how would I set that up to find the length of 3i plus 4j?
Square root of 3 squared, minus 4 squared,
So 3 squared, and what was the other part you said?
minus 4 squared, or plus 4 squared,
Yeah, plus
negative 4 squared.
-4 squared. Okay, so then that's our Pythagorean theorem. The negative is going to go away when you square it, so if we didn't have the negative on the 4th, not a big deal. And what are we going to get for a length? We're going to get 5. Okay, I've given you 2 examples so far where the length comes out nice. It doesn't have to come out nice. Okay, but the 2 that I have so far have been nice numbers. Okay, so our vector is 5 units long. Is it a unit vector?
Yeah. No, not yet.
Not yet, because for a unit vector, how long should it be? 1/5, right? Or 1 unit. So I have to scale it by 1/5. So take our vector and find that. That's what I want to find. So what would 1/5 of our vector be?
3/5, comma, negative 4/5.
And can you write it with the I and the J?
3/5 I, negative 4/5 j.
Yeah. That's what they're looking for. So that vector points exactly the same way as the original vector. All we did was make it 5 times shorter. So any question on finding a unit vector if I give you a vector to start with? So I told you there were 2 different applications. I mentioned 2 applications for vectors. One was velocity, one was force. We're not going to look at the force one. That gets into a little bit more physics and application than I want to do right now. So we're going to just look at the velocity example. So when you are writing a vector, remember a vector has 2 parts to it. It has a horizontal component, and it has the vertical component. We call them the x and the y components. Whether you write it with the I and the j notation or the other notation, right? There's always 2 parts to it. So what I'm going to do is I'm going to give you some information, and you're going to have to turn it into a velocity vector. I'm going to give you information like this. I'm going to tell you an angle that something's being thrown at and how fast it's being thrown. Now, when we write a vector, is there any spot in the vector that you plug in an angle?
Not really.
What?
really?
No, there's no spot for an angle. So you've got to turn this information into something that would work as a vector. That information, it's not directly giving you a vector. It's giving you the information you need to figure out the vector. Okay. So let's look at how we figure that out. So the first thing that we're going to assume is when we throw an object, normally it would curve, right? On Earth, it would come back down. We're going to assume when we throw it, it would just keep going straight. So it's like in outer space, okay? Not affected by gravity. Otherwise, it's going to get a little more complicated. So here's our object. It's being thrown. And the angle that it's going to be thrown at, we usually use a Greek letter to represent it and call it alpha or theta, whatever Greek letter you like. And when we write a vector, it has two components, a horizontal and a vertical. So we have to draw a picture there that's going to help us figure out the horizontal and the vertical. That's our object being thrown at a diagonal right now. What kind of picture do you think I'm going to draw here?
Triangle.
Yeah, I'm going to make a triangle out of that picture. The hypotenuse represents the object that's being thrown at an angle. And we're going to break it down into its horizontal and vertical components. It's a little longer than I need there, but that's fine. I've created a triangle. This is the horizontal component. This is the vertical component. So when you write the vector, you have to write down the formula for the purple arrow, comma, the formula for the blue arrow. That's how you have to write the vector. Okay. So basically, they give you the black. You got to figure out the purple and the blue. All right. Let's call this side x, and we'll call that side y. What trig function would involve this side, this angle, and this side?
And no. Cosine?
Cosine. Because cosine is, what's the formula for it?
Adjacent
Adjacent over
over hypotenuse.
hypotenuse. So we're trying to figure out a formula that's going to allow us to get the purple arrow. That's what we're trying to figure out. Okay. So cosine, what would we fill in
30.
for our argument?
30.
If the object was being thrown at 30 degrees, but we don't know a specific angle right now.
But that's what it said.
That's what we'll do when we get to that problem, yes.
Oh, okay.
But for now, what would we fill in?
Alpha.
Alpha, because we're trying to write a formula that's going to work for everything, right? So we don't want to put in anything specific yet. When we get to that problem, we will. Okay, so cosine of alpha equals, and then it's adjacent over hypotenuse. So the adjacent is x. And when I say adjacent over hypotenuse, what do I mean by hypotenuse? Like the what of the hypotenuse? The length of the hypotenuse. So you need to put this. We don't want to put adjacent over v. We want adjacent over magnitude of v. If you put adjacent over v, you'd literally be doing this. V is a picture. You don't want to put a picture in your denominator. You want the length of your picture, which is the length of the black arrow. Any question on why I put those bars there? We're not putting pictures in a fraction. All right, and now we'll solve that for x. How would we move the magnitude of the hypotenuse over to the other side?
Multiply.
Yep, multiply. And that is your formula for the purple arrow. It's the magnitude, which is the speed the object is being thrown at, times the cosine of the angle it's being thrown at. Okay, so when you write it as a vector, something like this with an I, plus something here with a J. Just move it down a little bit. What's going in the first box is that first formula. Magnitude, cosine, angle. Right, now we got to figure out a formula that's going to give us the number that goes in front of J, and that's going to be the length of the blue arrow. So what trig function would we use there? So we got to involve this, which will be given, that, which will be given, and that. Tangent is opposite over adjacent.
Oh, sine.
We need sine. Yep. So sine. Just doing the same thing I just did with cosine. Fill in the angle. And what would be my fraction on the other side?
Opposite of the hypotenuse.
And the opposite is,
9.
and what are we going to write in the bottom?
Magnitude of V.
Yep. Remember, if you don't put magnitude of V, you'd actually be drawing the picture of the arrow in the bottom of your fraction. We don't want that. We want the length of the picture of the arrow. Okay. And now we're going to do the same thing, get y by itself. How would we get the y by itself on the right side?
Multiply.
Yep, multiply. That is the formula for the length of the arrow in blue. Okay, that is the vertical component of the vector. So that is the formula for a velocity vector. Magnitude times cosine alpha gives you the horizontal. Magnitude sine alpha gives you the vertical. And remember, these letters are bold. Okay, just to be clear about what those are, the magnitude of V, that's the speed that they tell you in the word problem. So that's the speed of the object. Speed of object. And alpha is the angle they will give you that in the word problem as well, that you're throwing the object at. Okay, so you just fill in those two values, and we use a calculator and then figure it out. Okay, everybody have that formula? Okay, I think I wrote down the same thing again here. Angle, yep, that's the same thing I usually do. Okay, so now let's do that for our problem. We've got an object being thrown at 50 miles per hour at a 30-degree angle. Write the answer in unit vector form and then explain the meaning of each component, the horizontal and the vertical. Okay, what's the speed of the object in this one?
50 miles per hour.
50, and what's the angle?
30.
So we're going to take those two numbers and we're going to fill them in here and here. So 50 cosine 30, 50 sine 30. Okay, so 50 cosine 30. That goes in front of the I. Plus 50 sine 30, and that's going to go in front of the J. Yep. Okay, so we use our calculator to figure those out. So 50 cosine 30, I'm in radians, so we're going to make sure we switch back to degrees. Gives us 43.30. Go two decimals. I. And then 50 sine 30, that's going to be 25J. You type it in if you're not sure, but that's what you'll get. Okay, so that is the velocity vector. That's how you convert the information they gave you into a vector. You could also write it without the I and the J. They didn't want it this way in the problem. I'm just showing you how you could do it. That is equivalent, but they specifically said unit vector form. So I want that one. Okay. Now it says to explain the meaning of each component. What is the 43.3?
Horizontal.
The horizontal what?
Line.
So when you write a velocity vector, the numbers here do not represent a distance traveled. But the 43.3 represents something horizontal.
How far you're traveling to the right?
So it's not a distance. It's not a movement left, right, up, or down.
How many
Well,
How many units?
it is how many units of something, but I want to know what is it. 43.3 is the something you could measure, like if you actually did this problem, like if you fired an object at 50 miles an hour at a 30-degree angle, you could measure something in that problem and it would come out to 43.3.
Velocity.
What velocity?
The object.
Can you be more specific about the velocity of the object?
Moving forward.
The velocity of the object moving right, which is
Positive. I don't know. What are we looking for?
I know the velocity of the object is 50 miles an hour at a 30-degree angle, but 43.3 is the velocity of the object as it moves
To the air.
through the air. We're adding a few extra words we don't need. It's just the velocity of the object in which direction?
To the right.
To the right, horizontally. It's the horizontal speed of the object. So in other words, if this object was being fired like that, and you wanted to drive and make sure you stay underneath it the whole time, if you drove at 43.3 miles an hour this way, you would stay underneath the object the entire time. Does that make sense? Because it's going 50. But remember, it's not going 50 horizontally. It's going 50 up and to the right. Right? So that 50 miles per hour, that speed isn't all going into moving it forward. Some of that speed is going into moving it up. Okay? So same thing like if, let's say you were standing, right here, and you pointed a radar gun like that at that ball. Okay? If you pointed a radar gun at that ball, it wouldn't say it's going 50 miles an hour. Okay? If you stood up here and did that and pointed it down that way, then it would. But if you stand horizontally and point it, it's going to say it's going 50 miles per hour. I'm sorry, 43.3. Okay? Now, how about the other number? What's the 25?
The speed it's going at vertically.
That's the speed it's going at vertically. So now, same idea. If this object was going 50 miles per hour that way, and you wanted to make sure you stayed at the same height of the object the whole time, if you were in a helicopter, right here, and your helicopter was going up at 25 miles an hour, you would always be right next to the object. You'd be at the same height as it. Okay? You wouldn't want to go up at 50 miles per hour. You'd go ahead of the object. You'd want to go up at 25. All right, so it's just measuring the speed in each direction. All right. Any question on that? Okay, so section 5.5, again, more calculations we can do that are not something we're going to sketch. And we're going to look at what is called the dot product. So what we've done so far with vectors is we've taken two vectors and we've added them. We've taken two vectors and we've subtracted them. We've taken a vector and we've scaled it. What we haven't done is take a vector and multiply it by a vector. Okay, that's what we're going to look at in this section. So let's say we had those two vectors, and when we do an actual problem, you'll know what those numbers are. It'll be more like this. I'll give you the horizontal and the vertical components for each one. But for now, the horizontal components are going to be represented by A1 and A2, and the vertical components are going to be represented by B1 and B2. And those would all be different numbers. And what I want to do is take those two vectors and multiply them together with what's called a dot product. When we say multiply with vectors, you have to use a specific word when you say multiply. You either can say dot product, or the other one we could do is a cross product. So if you said to me, multiply these two vectors together, my next question would be which way? Dot product or cross product? There's two ways you can do it. We're not doing cross product today. Okay, we're doing dot product. So when you do a dot product, the symbol for it, first of all, is a dot. It looks like that. If you wanted somebody to find the cross product between two vectors, you would write it like this. That's completely different. Put a little cross between them. Okay, but we're not going to look at that today. So the formula for the dot product is very simple. You take the horizontal component from the first vector, take the horizontal component from the second vector, and you multiply them together. That's the first part. Now you take the vertical component from the first vector and the vertical from the second. You multiply those together, and then you add them up. And that is the dot product. So what I want to do is think about what kind of answer you get. We already know when you add vectors together, you get a vector. When you subtract vectors, you get a vector. When you scale a vector, you get a vector. How about when you find the dot product? Well, A1 and A2 are both going to be numbers when we do an actual problem. What do you get when you do a number times a number? You get a number. How about over here, a number times a number? You get a number. And if you take a number and you add another number, what do you get? You get a number. So when you do the dot product between two vectors, the answer will be a number, like 13 or -6. Okay, it'll be a number. It can be any number, positive, negative, fractions, decimals, or 0. But the point here is when you do the dot product, it is not a vector, it is a number. Okay, so let's take these two vectors and see if we can find the dot product between them. You think it's 1?
Yeah.
So we're going to set it up. What I'll do first is just write down my formula, and then I'll fill everything in. So I've got two things I'm going to multiply, two more things, and then I'm going to add them up. Okay. What are the first two things I multiply if I follow the order V first, then W?
2, 5.
Right. V first, then W. 2 times 5. So that's your horizontals. And now we're going to do the same thing for the verticals. V first, then W. So what would come next? Yep, -3 times 3. That gives you 10. That gives you -9. And 10 minus 9, that does give you 1. Yep. And that is the dot product. Yes, it's a relatively simple calculation. That one helps you to do something, which we'll probably see by the end of class. But for now, we're just going to practice the dot product. Any questions on how we got 1? All right, let's try the other way. W dot V. So this time, when we multiply, they want the number from W first, then the number from V. So what would we write down in our first set of parentheses? We'd write down 5 times 2. W first, then V. And in the second set, that's what we had up at the first one.
3, -3.
W first, then V. 3 times -3. But what happens when we do that?
Same thing as before.
You get the same thing, right? This is still 10, this is still -9. It still comes out to 1 even when you switch the order, which means it does improve. But I will tell you, this always works. You can switch the order and it never changes the answer. And what is that called when you can switch the order, when you get the same answer? So associative is one of them that we talked about. That has to do when you change the parentheses. This is commutative. Yep. So this shows us that the dot product doesn't really prove it, but it does work all the time. Okay, it is commutative. All right. Now let's try another dot product. This time we're going to find v dot v. We're going to dot a vector with itself. So just think of having 2 copies of the same vector. Okay, so for v dot v, what would be the first 2 numbers we multiply? 2. Yep. So you're just using the same number twice, 2 times 2. And for the next product? -3, -3. Yep. And what would be the dot product there? 13. Okay, so any question on finding the dot product? And I had another one, w dot w, but it's really the same as what we just did, v dot v. It's not the same answer, but same concept. Let's look at this one. So 2, 6, and 0, 0. So I've written the vectors a little bit differently. I'm not using the I and J this time, but we still do it the same way. Okay, so how about Jaden? What are going to be the first 2 numbers we multiply together?
Oh, what? Sorry, what?
To do our dot product here, what are the first 2 numbers we multiply together?
2 and 0.
2 and 0. Yep. Horizontal times horizontal. And we're going to do it in the order that it's written. 2, then 0. And the last 2 numbers?
6 and 0.
6 and 0. Okay. And what does that give me a dot product of? 0. And is that 0 a number 0 or 0 the vector 0?
0 number.
The number, right? When you do a dot product, we went through that whole thing where a number times a number plus a number times a number is a number. That is 0 the number. Now, when you find a dot product and the number comes out to 0, that means something special, which I'll tell you in a little bit. Any question on the dot product there? So distributive property, that's a property we're used to using when we do multiplication, and it works with vectors. If you have something added or subtracted in parentheses, you can take this u and you can distribute it. And again, you might think, well, yeah, you can always do distributive property. Well, you can't assume that because we know it works with numbers, we don't know if it works with vectors. And when we do cross product, you'll see that that is not commutative. So that'll probably be one of the first times you've ever seen in multiplication. If you switch the order, you get a different answer. So luckily with dot product, most of the things that you do know, they work. Like distributive, commutative, but cross product is a little different. Okay, so distributive property works. And the whole point of the dot product is that it helps you to find the angle. What do I mean by angle? I mean this angle. If you have 2 vectors and you want to figure out what the angle is between them, we can use the dot product. Now the formula that I'm going to give you, it comes from the law of cosines. Because the way that you could really figure out this angle right now is you'd have to draw that third side. And if you did this on graph paper, you would have 3 line segments, and you could find the length of each side using Pythagorean theorem or the distance formula. If you knew the length of all 3 sides, it would be a side-side-side triangle. We learned with law of cosines, if you know all the sides, you can figure out the angles with that formula. Well, there's a shortcut, so we don't have to find the length of all these sides, and we don't have to use law of cosines. Okay, the shortcut kind of does all that for us without doing all the steps out. There's 3 things you need to find when you want to know the angle. First thing you need to find is the dot product. That's going to go in the top of a fraction. And then in the bottom is going to go the product of the lengths.
Is U representing the non-product?
So U would represent one of your vectors. So like this vector over here might be U. This vector over here would be V. Just the name. Again, you can use different names for vectors, U, V, M, N, A, B, C. You don't want to use I and J. We talked about that yesterday. So this is the dot product between the 2 vectors that I give you. This is the length of U. And this is the length of V. So the denominator is the product of the lengths. The numerator is the dot product. And all of that is equal to the cosine of the angle. So that formula, I don't know if you remember the law of cosines, but that is a lot shorter. Law of cosines was much more involved. But that formula comes from the law of cosines. That's why there's a cosine here. So we're going to practice finding the angle between 2 vectors. We're going to start with just 2 random vectors. It's not going to be anything special. And what I'll do is I'll sketch them first, just to kind of get an idea of what we think the angle is. And then we'll actually calculate it and see if it matches our picture. Okay, everyone have the formula for finding the angle between 2 vectors? Okay. So let's try it with those 2 vectors. 4i minus 3j and 2i plus 5j. I think I have a graph. I'm going to make a graph. Okay. What I want to do is I want to draw them just to get an idea of what the angle looks like. And then we'll do it out and see if our work matches our picture. So 4i minus 3j. If I start at the origin, how do I sketch 4i minus 3j?
4 right, 3 down.
4 right, 3 down. 1, 2, 3, 4. 1, 2, 3. Yeah. Okay, so that's the first vector. And the second vector is 2i, 5j. How would we sketch that one? 2 right, 5 up. And now we're trying to figure out this angle right there. How much does it look like that angle might be?
Like 130, 140?
So if it was 130, if I just draw that in standard position, 135 would look like that. So if you look at that one in red, and I just rotate it a little bit, does it look like it's as big as that red one? No. So it's not as big as 130 or 140.
Like 100 degrees?
Yeah, it's probably somewhere around 100. It's a little bigger than 90. Maybe 95 to 105, somewhere around there. We can double check it if we, at least I think I can double check it. Let's see. Take that. And then make that a little bit bigger. Let's put that down right there. And then I think I can rotate this. Then I can rotate that. All right, so just kind of real quick estimate. I'm looking at the protractor. It looks like it's about 101, maybe 102, somewhere right around there. All right, so let's do it out and see if we get an angle that looks like it's about 100, a little over 100. All right, so first thing we need is the dot product. Okay, so Ruben, what are going to be the first two numbers I multiply for my dot product?
4 and 2.
Yep.
And 3 and 5.
4 times 2, and the second two?
Negative 3 and 5.
Negative 3 and 5. That's going to give me 8 minus 15, which gives me a dot product of how much?
Negative 7.
Negative 7. Negative dot product is perfectly fine. No problem. Never said the dot product has to be a positive number. Okay, so that's the first one. Next thing we need is the magnitude of the first vector and then the magnitude of the second vector. Okay, let's start with the magnitude of the first vector. It's going to be the square root of,
25.
and what's going to go underneath here to get that?
4 squared plus 3 squared.
4 squared plus, again, if you don't put the negative, not a big deal because it will cancel out when you square it. And that's 16 plus 9, which does give you the square root of 25. Yep. And the last thing we need for the formula is the length of the other vector.
Square root of 20.
Yep. So you're going to have 2 squared, 5 squared. And that's 4 plus 25, which is the square root of 29. Don't round it. Just leave that. All right, now we're going to fill those 3 numbers in. Right there. Cosine theta equals the dot product over the product of the magnitudes. Remember, we're hoping to get an angle that's a little over 100. That's the hope. So cosine theta equals the dot product over the product of the magnitudes. Now that's not the angle, that's the cosine of the angle. I need to get rid of this. How do we get rid of the cosine function?
Reverse cosine.
Inverse cosine. Take the inverse cosine of what's on the left, and then what happens there?
Cancels out.
These two cancel out, and what's left? Theta. And now do the same thing on the right. So that's what we need to type in. We have to be a little bit careful when we type that in on the calculator because there's multiplication in the denominator. So I'll show you how you do it. So inverse cosine. Whenever a denominator has multiplication like that, in order to have it do the order of operations correctly, you need to put it in parentheses. Just like I did right there. That's how you type it in. If you don't put parentheses, it'll either give you an error or, even worse, it'll just give you a number that's wrong. Okay? So we get an angle of 105.07 degrees. Which, for just sketching everything by hand real quick, that's about what we had. I had about 101, 102, but my protractor's probably not perfect on there. So any question on finding that angle between those two vectors? Now, 105, it's not really a special angle. It's just a random angle. What do you think we would consider to be a special angle? If it's 0, that would be a special angle we'll talk about. What else? 180, that's going to fall in the same category as 0, and there's one more. 360 would be the same as 0. 90. Yeah. So we're going to start with 90. What would that look like if two vectors had an angle of 90 degrees between them? Yeah, it would make a right angle. So when two vectors are perpendicular, or have a 90-degree angle between them, The word that they use to describe it is orthogonal. Okay, orthogonal means perpendicular. So on the test, if I ask you, are the following vectors orthogonal? I won't explain what that means. You need to know what it means. Are they perpendicular? Okay. Do they meet at 90 degrees? And you might see this symbol. This is the symbol from geometry for perpendicular. It's like a, sorry, upside down, capital T. So what did we just say the angle would be if they're perpendicular?
Orthogonal.
How much?
90.
90? So if they're 90, let's think about what would happen in our formula. Take the formula that we just came up with, and let's put a 90 in right here, and let's see what happens to the other side. So you'd have the cosine, and I'm starting with something that I already know is perpendicular. And I want to see what would that mean would happen on the right side. You'd have your dot product in the top, and then you'd have two numbers multiplied together in the bottom. I don't know what the dot product would be. I don't know what the two numbers in the bottom would be because I don't have an actual problem. All I know is I have two vectors that I'm saying are perpendicular, which means they have a 90-degree angle. There's lots of vectors that are perpendicular. I just don't have a specific example. Let's take the cosine of 90 and see what happens. Take the cosine of 90, you get 0. So you'd have 0 on the left, and you'd have this fraction on the right. So if two vectors are going to be perpendicular, this fraction has to come out to 0. What's the only way that a fraction could ever come out to 0?
Zero's on top.
If 0's in the top. And what do we have in the top right there in our formula? The dot product. Yep. So if the dot product comes out to 0, it'll make the top of this fraction 0, which makes the entire fraction equal to 0, which means the angle has to be 90. So there's a quick shortcut for figuring out if two vectors are perpendicular. All you have to do is figure out their dot product and see if it is 0. So I told you earlier that if it comes out to 0, that meant something special. This is what it means. Two vectors have a dot product of 0. They are perpendicular. And that's all you have to do. You don't have to worry about their lengths or the bottom of the fraction at all. You just have to find the dot product. If all you're trying to do is determine perpendicular. Okay. All right, so the question here, it's either a yes or a no. Are these vectors perpendicular? Okay, so find the dot product. And if they are perpendicular, the dot product will come out to 0. What's the calculation for the dot product here?
2 times 1.
2 times 1, just pretend there's a 1 when you don't see a number in front of a letter. So we have 2 times 1, and then we have 1 times 2. What's that come out to? 4. So are these two vectors perpendicular? No. What is the angle between them? That I don't know. I can tell you that they're not perpendicular. But if you want to know the actual angle, then you have to go back and do what we did on the last problem. Finish it off. Okay. But that's how you can quickly tell if vectors are perpendicular. So that's 90. That's a special case. And what were the other special cases we mentioned? 180. Okay, let's draw two vectors that have an angle of 180 degrees between them. That's an angle of 180. Do those two vectors cross each other? No, they don't cross. Like you could imagine, instead of putting that vector right next to it, imagine putting this one right underneath it. Put it right there. What do you think you would call these two vectors?
Parallel?
Parallel. Yep. So when you have an angle of 180, they're parallel. And now let's do an angle of 0. So 0 would look like this. it would be two vectors. I need two that are not glued together. That would be an angle of 0 degrees, because when you line up the initial points, there's no angle there to measure. So what do you think we would call these two vectors?
Parallel.
These are also parallel. So there's two cases for parallel. When they point in the same direction and when they point in opposite directions. That's 0 and 180. So what we want to do is look and see, is there a quick way to figure that out? So I'll do the same thing that we did for perpendicular. I'll start with an angle on the left. I don't know what the right will be. I'll just use squiggle symbol. And I want to see if we can come up with a shortcut. All right. So let's start with the case where the two vectors point the same way. And that's a 0 degree angle. Okay, what are my two vectors? I don't know. I'm just saying I have two vectors that point the same way. They have an angle of 0, so I filled that in. I would have a dot product in the top, and I'd have two lengths multiplied in the bottom, whatever they would come out to. Okay, let's type in the cosine of 0 and see what we get. Yep, we get 1. So now we have a fraction equal to 1. What's the only way that a fraction can come out to 1?
It's got the same numbers on the top and bottom.
Right, if the same number is in the top and the bottom, but you wouldn't know if the same number is in the top and the bottom unless you know the number in the top and the number in the bottom. So no, there isn't the same shortcut for this. You have to know the number in the top and the number in the bottom. That's the only way to know if they're the same. Okay. Well, let's try 180. So if your angle was 180, that means the two vectors point in opposite directions, but they are parallel. Dot product of your magnitudes, and the cosine of 180 is going to be -1. So you'd have -1 equals a fraction. How can a fraction come out to a -1?
It's got negative on one half, and then the numbers are the same.
Right, the numbers have to be the same, but one of them has to be negative. So you still would have to know the top number and the bottom number, right? In other words, the two numbers here have to be opposites. Well, you don't know if two numbers are opposites unless you know both your numbers. So you got to find both numbers. You don't have to do the inverse cosine part. So that is a little bit of a shortcut. But you still have to calculate the top, and you still have to calculate the bottom, and then just see, are they the same or are they opposite? So a little bit of a shortcut, not as much. Okay, so let's determine if V and W are parallel. Okay, that's the symbol from geometry for parallel. There's two vertical lines. So yeah, this is the last one. Okay, what's the first thing that we need to figure out?
Dot product.
Yep, we need the dot product. So a good space for that right here. Okay, first two numbers that we're going to multiply together. 4 and 20. Second two? -5, -25. 4 times 20. And -5 times -25. Okay, so there's my dot product. By finding the dot product, I can tell you one thing about the vectors right now. What do I know? Because the dot product came out to 205. The vectors are not. They're not 90. They're not perpendicular because I would have had to got a dot product of 0, yeah. I didn't get a dot product of 0, so are they parallel? I don't know. Are they perpendicular? Definitely not. Okay, but we have to keep going to see if they're parallel. Okay, so magnitude of v. What's going to go under the square root to do our calculation?
16 plus 400.
16 plus,
What's 12?
remember this is just vector v right now. 25.
Negative.
So we're not looking at the 20 and the 25 yet. We're just looking at the 4 and the 5. So 4 squared plus negative 5 squared. And that's going to give you the square root of 41. Yep. All right, so we get the magnitude of w and last magnitude of v. Now we need magnitude of w. What's going to go under that square root?
20 squared plus 25 squared.
Yep, so 20 squared is 400, and 25 times 25,
525? 625?
625. Okay, so now we got everything we need. We got the dot product, and we got the length of each vector. Now we just have to see if the dot product, which is what's in the top of the fraction, 205, comes out the same as the bottom, which is when you multiply these two numbers together. So we're hoping that that comes out to 205. If it does, then they are parallel. Okay, so square root of 41 times the square root of 1025 gives me 205. So I got a dot product in the top of 205. I got a product of the two lengths in the bottom of 205. And now I have something equal to 1. And we just did that right here. If you have something equal to 1, we know that the angle is 0 degrees. And we set up here, 0 means parallel. So the two vectors are parallel. So the answer to the question, yes, they are parallel. V and W. Okay. Any questions on that one? All right. So that's dot product. All right. So the homework, 2 separate pages. The first page is page 352, and that page is 7 to 15 odd. Each question has 3 parts. The first part is find the dot product. The second part is find the angle. And then the third part is to tell me if that is parallel, perpendicular, or neither. So all 3 parts are connected. Just finding angles. So there's 5 questions on the dot product. And then the other questions are on a little bit of review of what we did yesterday towards the end and today. 55 and 57 are the velocity vectors. And the 25 to 47, those are just odds. So 5 questions on the first page, and then whatever that adds up to on the second.